very specific details of how processes in individual molecular cloud to star formation in entire galaxies and in the universe, so very highly ionized gas outside of galaxies, and several other very important contributions. So if you want to know about cosmic chemistry, you came to the right lecture.
Okay, so thank you very much. I realize I'm at the end of the day. We all want to get going. So I'll try to stick to the time allotted to me. In fact, Raphael invited me to give a talk on chemistry in the cosmos, and he said, in 30 minutes. The universe is a big place. This is a schematic diagram of the cosmos. We know that it's expanding and dynamic, expanding out of a denser and hotter state, very, very dense state, to a period where the gas got sufficiently, the medium became sufficiently cool that it was already neutral. The stars began to form, galaxies emerged, and are continuing to emerge to this day. On this map, let me just put our location over there, Jerusalem in the center of the universe. Now we now have, interestingly enough, one of the big breakthroughs in the last couple of decades is that we now actually have a standard model of cosmology. So we're actually able, we now know that how to divide the mass energy of the universe into component parts. The fractions and the different components evolve with time. So at the time of recombination, around 13.7 billion years ago, this was the distribution, and this is what it is today. So most of the universe is, in fact, in this mysterious form called dark energy, which is leading to the accelerated expansion of the universe today. There's dark matter, which is better understood but still mysterious and has structure to it. And then there are the atoms, which are 4.6% of the universe, and chemistry is in there. And so I'm going to be focusing on this little wedge and its evolution. Well, it's really remarkable to show the periodic table in terms of how the elements actually emerged. We know that hydrogen and helium were formed in the early stages in the first 3 minutes, but the rest of the elements in the periodic table were produced nucleosynthetic processes in stars. And in this diagram, color coding shows which kinds of stellar processes, which kinds of stars the elements were formed in. So exploding massive stars, exploding white dwarfs. And of particular interest in the past year is our understanding, it was a very dramatic understanding and discovery in the world of astrophysics, is that the purple elements, the R process elements, those that are produced by rapid neutron capture faster than beta decay, were almost certainly produced in very dramatic mergers of neutron stars. There was a very major event in the last year where two neutron stars merged, releasing gravitational waves, which were then, gravitational waves which were then actually detected. Prior to this event, gravitational waves were detected in black hole mergers, but this was the first time that a non-black hole system was observed in gravitational waves, and this is a very dramatic event. These events, at their peak energy release rate, release as much energy as all the visible stars in the universe combined, rate of energy release. Neutrons get ripped off, and these elements are made. Yeah. Another important table is this list of abundances that result from all of these processes. So most of the elements are hydrogen and helium with small amounts of carbon, nitrogen, oxygen, and other important elements for us, oxygen being the most abundant heavy element. So my talk roadmap, I'm going to talk about very different kinds of phenomena, giving you a flavor of this field, of how molecular astrophysics informs us about a whole wide range of phenomena in the evolving universe: galaxies, interstellar medium, star-forming clouds, protostars, planetary disks, all the way to planets. And it's molecular chemistry all the way. So let me start with this picture, which is a Hubble Space Telescope image of a relatively nearby galaxy. It's only 20 million light years away. This galaxy is actually similar to our own Milky Way galaxy, a spiral structure, and what you see in this picture are the white stuff is starlights, stars similar to the sun. You also see brown stuff, which is actually interstellar dust, and then these red spots, which is photoionized gas around hot stars. An important thing about galaxies such as this, our own Milky Way, which many non-astronomers are not aware of, is that star and planet formation is an ongoing process, even today. For example, the Milky Way galaxy is forming stars at a rate of about 3 solar masses per year. There's a black hole in the center, and a very massive black hole, million solar masses, and I'll mention black holes a bit later. A key thing about star formation in galaxies is directly associated with molecular gas. So what I've overlaid here is a beautiful recent interferometric image of millimeter wave rotational, 1-to-0 rotational line emission of carbon monoxide. And you see it perfectly correlates with where the stars are forming in this galaxy. CO is a primary tracer of molecular gas, mainly because molecular hydrogen, which is of course much more abundant, is usually very difficult to detect directly. Let me then go into our galaxy and look at a single individual star-forming cloud. So this is a famous dark cloud, so-called Barnard 68. And when these were first seen in the late 18th century by William Herschel, he panicked, and he cried out to his sister, "Mein Gott, da ist ein Loch im Himmel." He said, "My God, there's a hole in the sky," looking at all these stars. This is this dark thing. It looked like, what was that, you know? So he was frightened by it. We now know this is actually a cloud of gas in which there's sufficient amount of dust that actually blocks the background starlight. This particular cloud contains about 2 solar masses of molecular hydrogen and is on the verge of gravitational collapse to form a single star. This is a very early stage of star formation. You can actually observe it in the infrared, and infrared light penetrates through, so you can see, so Herschel can relax. There are stars back there. And this is actually, you can actually see sort of like sunsets. Everything's turning red behind there. And this is called reddening of starlight. And this is a phenomenon due to the absorption of the light by silicate and carbonation, dust grain, submicron size, all the way down to the molecular scale. One of the important measurements from the 1990s using the Infrared Space Observatory is this spectrum. It shows a large number of solid-state molecular absorption features due to ices coating the inner parts of the silicate or carbonaceous grains, as shown in this cartoon. So you have ammonia, carbon dioxide, water, methane, methanol, methane, methane here, formaldehyde and water and things like, and CO, of course, and H2. The ices play a major role in the evolution of star forming and protoplanetary disks, as you'll see. Here's another pretty picture zooming in on the inner part of the star-forming molecular cloud in Orion. This is about 1,500 light years away. It contains hundreds of young stars, including the central trapezium stars that were first observed by Galileo. This is 10 light years across. This is a 3.6 to 8 micron image done with the Spitzer telescope showing dust emission in the red there. Let me just summarize some very key facts about the molecular interstellar medium. First of all, the ISM is multi-phased. It's turbulent. It's energized by optical and UV starlight, shock waves due to supernova explosions, and also cosmic ray, very energetic particles called cosmic rays, which are also produced in supernova explosions. The relevant molecular cloud densities that are typical are very, very low compared to anything that we're familiar with in Earth laboratory experiments, ranging all the way from 100 to 10 to the 7 particles per cc. So this is much lower than you can achieve in the best laboratories. Temperature is very low, from 10 up to 1,000 degrees. The other fact is that the ISM is dynamic, very far from thermodynamic equilibrium, and the chemistry is not anywhere close to thermodynamic equilibrium. It's actually functioning in a 2-body kinetic limit, as I'll talk about. So here's a famous recent scan, high-resolution spectral scan of the same region, showing a huge number of molecular species, including water, which is, I'm going to touch on more deeply in a minute, of course, is a big topic of this meeting, and a very beautiful array of organic molecules. You can see there's a very rich spectrum. In fact, we're now reaching the point where we're sort of in the confusion limit and trying to identify more and more molecules. Here's a complete list of all the interstellar molecules detected to date, starting basically from the emergence of millimeter wave spectroscopy in the late 60s and early 70s to the current time, starting with molecular hydrogen here at the top and a large number of diatomics, to more complex molecules, 3 atoms, HCN, which I'll say something about, and water somewhere down here, to much more complicated organics with different kinds of structures, linear, linear molecules or something like cyclic molecules. This is cyclopropionidine. And let's see, this one we'll be enjoying very shortly, this one over there. And interestingly enough, also fullerenes have been detected. There's an interesting story, which is a lecture in of itself, C60 and C70. C60 was detected in 2010, 25 years after Kroto just made it in the lab, motivated by his desire to understand some of these 10 atom species. You can also arrange them in an organic, in this way. So there are different types. And what's interesting historically is that some of the species in that list I just showed you were discovered in the interstellar medium prior to synthesis in the laboratory. So a famous case is the formyl ion, and here are some other examples. There are also many isomers. Okay, so you have methylformate, acetic acid, and glycoaldehyde, which is supposedly sweet tasting. And many isotopes. I did not put down all the isotopic varieties in that list. There are many isotopes, of course, water and heavy water. What's particularly interesting astrophysically is that the chemistry responds to specific stages of star and planet formation. So let me begin at the beginning. This is arguably, I call this a chemical reaction, two-step chemical reaction network. It's the simplest network you can imagine. Arguably the most important reaction sequence in the history of the universe, because it was this process in the early universe that enabled the formation of the first stars. You needed to cool the gas down to enable fragmentation and cloud collapse, and this required the formation of molecular hydrogen. Formation of molecular hydrogen enabled cloud cooling via rotational vibrational emissions. And once this occurred, by the formation of the interesting anion H-, hydrogen with two electrons attached, stars could form, and this led to the ultimate production of all the heavy elements. Let me just mention as an aside that H- is a fascinating anion for other reasons. It actually dominates the opacity in the photosphere of the sun, which then, therefore, by Kirchhoff's beautiful law, means it also dominates the emissivity. So effectively, although you're seeing black body radiation when you look at the sun, 5,000 degrees, the photosphere, what you're effectively seeing is H-. So when you look at the sun, you're seeing H-. Another fact about interstellar chemistry is, although this is an inefficient process because it's a radiative process, it's slow, it enables star formation, but in present-day galaxies, H2 doesn't form this way. Usually it forms on the surfaces of dust grains. This is a cornerstone of interstellar chemistry. I want to mention it briefly. This famous protonated molecular hydrogen H3+ with this beautiful triangular structure as first understood by Coulson. And H3+ is a crucial ion in interstellar chemistry. You first ionize a hydrogen molecule with an energetic cosmic ray proton. The H2+ reacts immediately with H2. It's just very fast to make the H3+. H3+ is stable, but it does dissociatively recombine, so this is the removal mechanism. So you build up an equilibrium abundance of H3+ by the balance of this reaction with this reaction. Once you have H3+, it actually acts as a universal proton donor, effectively an acid, because any heavy element, CNO, sulfur or silicon, will react with the H3+ and produce an XH+ ion, which then leads to a whole chain of chemistry. For example, water. So I want to mention water, because it's obviously, we've talked about water a lot, but where did it all come from? Well, it was formed actually in the interstellar medium in 3 different ways, which I can describe here. And there's a lot of physics and physical chemistry here, but let me just describe it schematically. You start with an oxygen atom. You react with H3+, the way I just described to make OH+. This is reacts with H2 down to H2O+, down to H3O+, which is a saturated ion. This will then recombine with electrons, making water or OH. So there are these basic processes, which are all well understood. And this is the way we make the water. Of course, one also has to worry about photodissociation by optical UV starlight. And these are the back reactions that remove the water. This is the primary gas phase mechanism for the production of water in the universe in the low temperature limit. If you go to a slightly warmer region, the warmer area, then you can directly go from oxygen to OH to H2O directly in this way, but these forward reactions are endothermic, and so the gas has to be sufficiently warm to enable it. And then there are the back reactions, and of course, UV photodissociation. So this is the gas phase. On another system of reactions that are essential are the grain surface reactions, which are essentially hydrogenation. So hydrogen atoms land on the dust grains, they move around, they meet oxygen atoms. The molecular hydrogen also form on the dust grains, leading eventually to this complicated looking network, but it's not really that difficult. In the end, you wind up with surface water, surface ice, which can then be desorbed into the gas phase or then also freeze out back in this way. So this is what you see here is basically the chemical theory that goes into all of the present day modeling of water dynamics in space, in the interstellar medium. So let me apply this theory. This is an example of a protostar, what's called a class 0 protostar. It's a star which is just forming inside a cloud which is still obscured optically. This is an infrared image. You can see here this is the start of a circumstellar disk. This is it's 1,000 times bigger than the solar system. And this phenomenal jet, this is an outflow jet 1 light year across. Jets typically form in astrophysical environments which are accreting because there has to be some kind of angular momentum loss. The jets carry away the angular momentum. So this is an image in molecular hydrogen. A very beautiful result is this, which is the same jet but now imaged in water emission. So this is a 179 micron emission of ortho H2O. This upper state is 114 degrees above ground. This is warm water chemistry in operation here due to the shock heating along the jet. And one can quantify the outflow rate. It's about 1 Earth ocean per 5,000 years. So that's not good for the planetary system forming in there. So not all the water escapes, but that's what you see in this beautiful outflow. And it also turns out that the water is actually a major coolant. The rotational emission lines, such as this one, are cooling the gas and contributing to the way the shock waves evolve through the jet. I mentioned water. I'm mentioning water here, and I just have to talk about this. Water in interstellar medium was discovered by Townes and his group in 1969 via this 22 gigahertz transition, which is a little bit higher up in energy. And it was quickly realized that something very interesting is happening with this transition, because it turns out that if you look at the molecular behavior of the rates of transitions that are occurring between the levels, this particular level has a very rapid spontaneous rate of decay rate relative to what this upper level is doing. And this actually leads to a population inversion. This leads to a population inversion, which then creates essentially a natural laser beam. So this transition is able to amplify its own radiation or background radiation. And so you wind up in some situations with an emission line with a strength, with a luminosity of up to 1,000 solar luminosities in a single spectral line. So that's a 10 to the 30 watt laser. And that, this is a beautiful tool in addition to a beautiful phenomenon, as I'm going to show. And I always like to show this paper by Albert Einstein, 1916, which is a four-page paper, which it's in German, but all students should read it, where he actually, for the first time, showed that simulated emission could exist, but he probably would not have been able to dream that actually Townes would actually invent a laser and also then observe it naturally in space. But what's interesting is that these masers can actually be used as dynamical probes. And a famous example of this are the relationship between water masers and supermassive black holes that I mentioned at the start of my talk. There's a galaxy, NGC 4258, 135,000 light years across. It has a supermassive black hole in the center, as all galaxies of this type do, but it's accreting material, and it's actually an active black hole. But what's amazing is that one actually can use these masers to actually measure the black hole mass. And the way because these maser spots, which are about the size of a solar system each, are so bright that you can actually observe their individual motions across the sky using techniques of so-called very large baseline interferometry. It turns out there's effectively little maser spots which are orbiting around in simple Keplerian motion, and one can observe directly their velocities, their radial velocities here at the edge, and also their angular accelerations across the sky. Then it's a simple high school physics. If you know these two quantities measured, you then can infer the actual physical size Once you know the physical size, you've measured the angular scale, that gives you the distance. And you know the distance, you know the mass of the black hole. So this technique of using water masers dynamically is one of the best measurements, or most precise measurements of the mass of central black hole in galaxies. Well, I mentioned a Keplerian disk, so this moves, speaking of Kepler, then I have to say something about exoplanets and protoplanetary disks. So we now know that there are thousands of exoplanets. We know that these have been detected in all sorts of different methods. And here's a plot of the size of the planets versus their orbital periods, and we can divide them into these different subgroups, including hot Jupiters, Jupiters which are close to their parent stars, or cold gas giants like our Jupiter, rocky planets like ourselves, lava worlds, and then undetected planets. And these planetary systems evolve out of protoplanetary disks in which the planets form. Let me just show you one method of detecting planets. This is direct detection. So here's a famous direct detection. It's a star called HR 8799. There's a star in the middle, and these four planets are Jupiter-like, but they're sufficiently warm that they can be detected in infrared, and not only that, they can be followed. So here are the planets orbiting that star. So there are four of them. Well, let me just mention one very, very famous instrument, which is the greatest, what I call the great astrochemistry machine, which is the Atacama Large Millimeter Array in Chile, run by Europe, USA, and Japan. It's a system of 66 12-meter antennas that operate as a single telescope, as an interferometer. And the amazing thing is that it achieves resolutions of about 0.01 arc seconds at 1 millimeter. 0.01 arc seconds, just to give you a sense of what that is, that's basically being able to resolve from here 10 meters on the surface of the moon. If you look at the moon, you could see something which you could resolve something which is 10 meters across at that resolution. It's also extremely sensitive. I think the most important results of ALMA are, there are several different areas of astronomy, but where ALMA is contributing, including extragalactic astronomy. The most important has to do with protoplanetary disk evolution. So let me show you an example of this. This is a protoplanetary disk observed pre-ALMA. It's a pretty remarkable image because it's spatially resolved. Notice the scale here. So this is 100 astronomical units, where one astronomical unit is an Earth-Sun distance. So I'm now talking about much smaller length scales than I did before. This is 1.6 times 10 to the minus 5 light years, or 8 light minutes. This is 100 AU. This was the best pre-ALMA. We turn ALMA on, that's what one saw. And this is really a stunning image, which really made the news. And what's interesting here are these gaps that appear. And we still don't fully understand what these gaps are, but there's a strong possibility that these gaps may have been opened up by planets in formation. If that's true, then that means that planetary formation is very efficient because this whole system is only 1 million years old. So it's quite remarkable. But what's even more amazing is that one can actually now do molecular spectroscopy of these disks. So this is not continuum emission, this is now line emission in the deuterated formal ion. So this is 3-to-2 line emission, ALMA image in another disk, and you see this interesting two-ring structure. This two-ring structure can actually be understood chemically in very simple theory, which I can try to write down. And here it is, so let me just explain this. The first step is this one. So I mentioned H3+. H3+ can react with deuterated molecular hydrogen in this direction, doing a proton transfer, or can go back in this other direction. But the thing is that the zero-point energy of this ion is lower than H3+. So if the gas is sufficiently cold, you'll preferentially go in this direction and then build up an H2D+ abundance, which is much higher than the deuterium, the cosmological deuterium abundance, which is 10 to the minus 5 or so. So once you have this H2D+ in the gas, and you're able to get CO off the ice, you immediately react in this way to make the DCO+. So this is around because the gas here is cold, and then the CO has to come off the ice. And this is the first place where it comes off the ice. This is the snow line. Out here it's frozen. Here's where it's starting to come off, to evaporate off the ice due to just thermal heating. In here the gas is too hot for fractionation to proceed, so this disappears. And out here you have non-thermal CO desorption. So this is a, what am I doing? I'm pushing it on. So this is a very sensitive chemical probe enabling detailed studies of the molecular physics of these disks and their evolution. That's a frontier area now in molecular astrophysics. Another example is these beautiful spectra of nitriles in the MWC480 disk. So this is work by Karin Oberg, showing in which she detected CH3CN, HC3N, and HCN in this disk. And these double peaks are signature of the Keplerian differential rotation. The disk mass is about 0.2 solar masses. The radius is 81 astronomical units with a mid-plane temperature of 23 in this system. And remarkably, the abundances of these nitriles relative of these relative to HCN, very similar to what's seen in solar system comets. This is a very strong hint that the cometary evolution, the protoplanetary evolution in our solar system is similar to MWC480. Let me just wrap up this very quick tour with this interesting statement. HCN is actually famous, of course. Hydrogen cyanide was discovered by the Germans. They called it Blausäure. Then it became prussic acid and hydrogen cyanide. But HCN is actually important for the emergence of life, because there are quite a few ideas that actually HCN may be a very important precursor feedstock for the emergence of early Earth RNA world. It's work by Sutherland and others. And so seeing HCN in these disks, and then their appearance also in comets, and then arrival on Earth, is actually a big story, which is really what this whole field is all about. And there are many grand challenges here, especially in this part of the arrow here. So I think in the next 10 or 20 years, the relationship between the disks and the planets which are forming is going to be filled in. Of course, then there's this whole question of the origin of life and us. So let me conclude there. Thank you.
In your first slide, you show that the early universe had more atoms than now. 12%, and then 4.6.
It's the relative amounts. It's not the relative fraction of the mass energy. It's not that.
Okay, well, what causes a decrease?
Well, it's basically it's the behavior of how the different mass energies evolve with time as the universe expands. The universe is expanding, and so the mass densities of the different components evolve in a different way with the so-called scale rates. For example, simple example is just comparing radiation with matter. So they evolve differently, and so the radiation is the thing that fades away the quickest. The dark energy, for example, comes in at sort of a steady rate. Initially, it's very small, but then as all the other mass densities of the other components decrease with time, that thing is sort of staying constant, and suddenly just takes over. So we're actually now in a very frightening, from my point of view, a very frightening phase. In the simplest picture of the evolution of the universe, everything is going to become causally disconnected, and everything's going to disappear from everything else. And in my cosmology course, I call that the Alzheimer universe.
Now that you have mentioned dark energy, would you care to say some words about dark matter? Yes.
Well, we don't know what it is, but we know it's there. Okay. By the way, I'm amazed by these questions because this is not chemistry. The chemistry isn't the 4%. Well, we don't know what the dark matter is, but we know that it must be there. We know that there are lots of pieces of evidence showing that dynamically. Basically, what dark matter is, observationally, is basically effective gravity of unseen matter. And there's very strong evidence that it really is a separate component relative to normal matter. There's several lines of evidence. The strongest piece of evidence actually from the sound waves and the cosmic microwave background radiation. Okay, but what is the, yeah, one more question.
Let's take one more.
Thanks.
Somewhere you showed a slide that was a marvelous collection of molecules from C11 all the way down to C1, which is more than enough to make anything one wants in principle. But you can also make a lot of those things from cometary, comets impacting, from lightning strokes, from all kinds of other stuff. Do we have any measure of the relative rates of arrival on Earth's surface from these various sources?
Well, most of those, for most of the molecules in my list, I would say no, for sure not. I think there's thinking that water, I mean, that's on my list, maybe the most interesting one. There are thoughts that actually the water that's on Earth came from the outside, as opposed to in situ. And that, I don't think that's a fully settled issue. I think the strongest evidence was from the deuterium abundances. But yeah, I mean, so.
But just take HCN. Do we have more HCN falling in from the Kuiper Belt and from wherever? Do we have more HCN?
Yeah, okay, George, that's a grand challenge.
Okay.
That's in my little arrow. That's it. Yeah.
I'm told that we have to finish, so perhaps we should.
We want to go consume CH3, CH2OH. That was on my list. Yeah.
Okay, so let's thank the speaker again.